Welcome to another podcast. In this episode, we're going to be taking a look at how we transfer the idea of effective rates and compounding more often per year and translate that into a completely new formula that describes what's called continuous compounding. Now, I want to start by looking at a couple of different values here. So suppose let n represent the number of compounding periods per year, and let the right column is going to describe the APY. So suppose that I'm looking at a rate where if I compounded once per year, the nominal rate or the stated rate in the problem would be 3%. So if there's only one compounding period per year, then the APY is the same as the stated rate. Let's say that I compounded twice per year. If I calculated the APY in the case where I compound twice per year, then the effective rate is going to be slightly higher. In this case, it's 3.023%. If I compounded quarterly, you can go in and check these values. We would get 3.034%, so we're still going up. If I compound monthly, that would be 3.042% for the effective rate. If I compounded 52 times a year, in other words, weekly, then the effective rate for that problem would be given by this. If I was to compound every day, in other words, add the interest into the account at the end of every day, then effectively over the course of the year, I would earn that much on my investment. Remember, the APY is the percentage change in the investment per year. Finally, if I was to look at compounding 8,760 times per year, this would be hourly. If I was to add the interest in at the end of every hour, then the effective percentage increase per year in the account would be given by this. And what I want you to notice with this example is, yes, we do increase the effective rate, but we have diminishing returns on that. Now, I talked about this in a previous video, that as the number of compounding periods increases, the APY increases, but with diminishing effect. I was getting change in the hundredths place initially, then in the thousandths, and now it's not changing until the 10,000ths of a percent. It's a very, very small difference between, say, compounding daily versus compounding hourly. But what this video is about is, what if I was able to or wanted to interpret compounding an infinite number of times per year? What would the APY be in that case? Well, let's remember that the APY formula is given by 1 plus r over n to the n minus 1. And what happens as n goes to infinity, and so this is a little bit of calculus coming into play here, it turns out that the quantity that I have boxed in green here, so this quantity here, it turns out that that quantity becomes e to the r. So we get e to the r minus 1 is the APY when n is infinity. So what is e to the r? Well, e is the constant, the exponential constant e, which is approximately 2.718. And then you could keep going with decimals. It's an irrational number, which means its decimal expansion never repeats. You can't express that as a fraction. It's like pi. So it's just a number. R is the same r as was here. So this r is the same as this. They just have different interpretations. This would be the continuous compounding rate, whereas this would be the n compounding rate for whatever n is. It would be monthly or yearly or whatever. But the point is, if I wanted to calculate the APY, I would use e to the r. R is 3% or 0.03 minus 1. And if I calculate that value, it gives me 3.0454534. And this decimal keeps going, of course, but cutting it off there, we get that much percentage. So we don't have any change between hourly and all the time, except out to the, it looks like the 5th decimal place. So at the 5th decimal place is the first place where we get any sort of difference between compounding hourly versus compounding continuously. So the question is it practical to compound continuously? And the answer to that's yes. Compounding continuously represents any sort of problem where rates are changing constantly. not necessarily rates, but where the value of something is changing constantly. And we actually have a really good example of that in everyday life. Continuous compounding describes inflation. So if I wanted to look at a problem involving inflation, inflation is the change in value of goods and commodities over time due to increase in prices, decrease in goods. There's lots of things that go into determining inflation rates, but continuous compounding is a great way of describing those. And so if I take my compound interest formula, which is P times 1 plus R over N to the NT, and I let N go to infinity so that I'm trying to describe continuous compounding, then the piece that's in the green box, so you can look at it here as well, the piece that's in the green box gets changed to this e to the r. So my new formula would be A equals PE to the RT. So this is the continuous compound interest formula. So this represents continuous compound formula, continuous compounding. So I have an example that I want to apply it to. Suppose that we know that the continuous inflation rate is 3.5%. So all the time things are constantly changing at a rate of 3.5%, which means yearly they're changing at a slightly more than compounding things hourly rate. How much did a pizza cost 40 years ago if it costs $10 now? So I kind of want to work backwards. Something that costs $10 today, what did it cost 40 years ago if goods and prices have been changing continuously at a rate of, in this case, 3.5%? So for this particular problem, I'm going to use my PERT formula here. And I'm assuming that the only change in the price of the pizza is due to inflation. So just listing out the pieces that we have, A is the price of the pizza in the future, which would be 10. So it's $10 in the future. P is the principal value, which was the original pizza price. And then E is not a variable. E is this constant, okay? E is not a variable. R is the value, in this case, corresponding to the rate. So the rate here as a decimal is 0.035. Remember, this represents 3.5%. If we're sticking it into a formula, we're going to use the rate. And then the time in years, once again, so this T is the time in years, is 40 years. And so for this problem, I want to know what initial amount will grow to $10 after 40 years. So my formula looks like this. 10 equals PE to the 0.035 times 40. And we want to solve for P. So the principal amount, or the pizza price, would be 10 divided by this amount. So we can easily do that in the calculator. Now let's just make sure that we have the right things going for us here. I want to do 10 divided by, and in order to get this exponential correctly, what I want to do is take E and raise it to the 0.035 times 40, making sure all that's in the parentheses there for the exponent. And then when I solve, I get that the price of the pizza is $2.47. So this is $2.47. So a pizza that cost $2.47 40 years ago would be worth $10 now at a continuous inflation rate of 3.5%. So I also asked the question, what is the price if we assume an annual inflation rate? Well, if I'm assuming annual, then annual wouldn't be n equal to infinity, it would be n equal to 1. And so if I assumed an annual inflation rate, then I would have 10 equals P, 1 plus R is 0.035, n is 1, to the 1 times T would be 40. This would be the formula that I would be working with. And we could easily solve for the value P here, and if we do, we'll get $2.53. So this just goes to show you it doesn't make a huge difference to calculate things continuously versus, in this case, annually, but there is a difference. essentially all we've done, and so I want to make sure that you walk away with this, essentially all we've done is exchanged the items in the green for the items in the red, and all we've done there is the items in the green are the b value for some exponential equation, and this is also the b value for some exponential equation. And so the idea is we're just changing the growth rates in the problem, the common ratio in the exponential models, to accommodate annual increases versus continuous increases. So it just leads to a slight difference in the problem. You can see what I mean by slight. The difference between compounding annually and compounding continuously in the case of 3% is very, very minimal amount. So we're just trying to allow for those increases in compounding to occur. All right, thank you for watching.